Hello, I'm Justin Huey doing problem 6.1 from the textbook, in which we are given this circular loop and we're asked with a current running through it, and we're asked to find the torque on a square loop a distance r away that also has a current running through it. We're told that this distance r is much greater than a, the radius of the circle, and it's much greater than b, the side length of the square. Okay, so first things first, we know that magnetic dipole moment of the circular loop could be found using the right hand rule. So as we're going around the circle, as we place our thumb in the direction of the current, we know that the dipole will be coming up through the center of the circle, so giving us our M circle in the z hat direction. And we could do the same thing for the square loop, same kind of thing. So we could see that the magnetic dipole moment will be protruding through the center of the square loop in the y hat direction. So M square will be going as so. Okay, so first let's calculate those values. So we know magnetic dipole moment is equal to current I times the integral dA. So M circle will evaluate to I times its area, pi a squared, in the z hat direction, and M square will evaluate to I b squared in the y hat direction. Okay, and so now we know that torque is equal to the cross product of the magnetic dipole moment times the across its magnetic field, or across the magnetic field. So first we need the magnetic field due to the circular loop. So to find that, we know that this equation will give us the magnetic field due to when it has a magnetic dipole moment at the origin, that's points in the z hat direction, which luckily we have. So we could say that B is equal to mu naught times M circle over 4 pi r cubed times 2 cosine theta in the r hat plus sine theta in the theta hat direction. All right, which is equal to mu naught IA squared over 4r cubed, the pi's cancel, times 2 cosine theta r hat plus sine theta theta hat. Okay, now let's draw this on our figure. So we know radial direction, radially outward from the circle, will just be in the y direction. So there we have our r hat. So b of r goes that way. And we know from theta, and theta hat goes in the direction of increasing theta. So b theta will be straight down negative z hat direction. All right. So now we could do this. So now we know that the torque is equal to M cross B. Okay, so we know that M square is in the y hat direction, which we'll say r hat, and we know that the r component of our magnetic field, BR cross r hat, will just give us 0. So we don't need to worry about the r hat component of our magnetic field. We only have to worry about the theta hat component. And thankfully that sine theta, since we are at pi over 2, that sine theta will just evaluate to 1. So we could ignore it, or we don't have to worry about it, I should say. That gets us to n is equal to, we have magnitude of M squared, magnitude of B, and sine of the angle between them, which luckily that angle pi over 2, so we'll just evaluate to 1. And now we need to find out the direction of our torque. Well, we know we have y hat, as we said, M squares in the y hat, so y hat crossed with negative z hat will give us negative x hat. Okay. So now plugging in or making our substitutions for the actual values, we are going to get I b squared times mu naught I a squared over 4 pi r cubed in the negative x hat direction, which just simplifying or combining terms, mu naught I squared, A squared, B squared, over 4R cubed, all in the negative x hat direction. All right, so there we have our torque. Now we need to visualize this. So our torque is pointing into the page, which we know that if it's, so we know that the rotation will be curled around, so we know that the torque will be moving as so. So that's our torque. So what's this going to do is this is going to cause the square loop to reorient itself. So if we're taking this as a side view, and in time we're going to see it to where this, and we'll know in this case we'll have m squared going this way, and it'll go to this case where m squared is going downwards in the negative z hat. So why does this happen? So the final orientation where the final orientation it reaches is because the torque is working to align itself, the magnetic dipole moment with the magnetic field. And when the magnetic field comes into alignment with the torque, or I'm sorry, when the magnetic field and magnetic dipole moment come into alignment, the torque will be 0, because as we said, the torque is equal to the cross between them. So when B's like this, because B's not changing, so that means that B will be like as so, and it'll be aligned, so the torque will stop acting on it. And even if it were to keep going and overshoot, then even if it was going to keep going and overshoot, the torque will start acting on it again in the opposite direction to realign it. And even if it was to oscillate, it would stop. It would come to rest where m squared is equal to, it'd come to rest where m squared is equal to I b squared negative z hat. That's be its final orientation. I hope that helped. This is it for problem 6.1. Thank you.